Right, let's go ahead and look at the discussion question number three. So we wanted to set up an equation that models this situation here. So we have a 400-gallon tank. So that's the volume of this tank when it's empty. Initially contains 200 gallons of water with a concentration of 2 picograms per gallon of dioxin, a dangerous carcinogen. We have water. So let's draw. Here's one of my many, many bad pictures. So here's my tank. It's half full initially. Okay, so there's something coming in. There's something coming out. So it's all I know so far. We know water containing 5 picograms per gallon of dioxin flows into the top of the tank. I did side at a rate of 4 gallons per minute. The water in the tank is well mixed, and 2 gallons per minute are removed from the bottom of the tank. How much dioxin is in the tank when it fills up? Okay, so so we've done a few of these mixing problems before. I think in these problems, it's probably more straightforward, even if it takes a little longer to model this as two different rates. So let's figure out what the variable is first. So we are asked about how much dioxin is in the tank when it fills up. So that dioxin, the amount of dioxin in this tank should probably be a variable I control for. So let's call that D. So dd dt. And I'm going to break that down into two rates. dd in dt minus dd out dt. Okay, so what is coming in to this? Actually, before we go do that, let's talk about what units dddt should be expressed in. So D is the amount of dioxin. How am I measuring dioxin? So I'm measuring D, that is dioxin in water, and I'm measuring that in picograms. And then T, that is time elapsed. And what am I measuring that in? That is measured in minutes, which means that this rate dd/dt needs to be measured in picograms per minute. So, and I'm writing that down because we want to keep consistent. So what is dd in dt? So what's coming in here? Water containing 5 picograms per gallon of dioxin flows in at a rate of 4 gallons per minute. Okay, so what's coming in is 5 picograms dioxin per 1 gallon of water. And this is part of why I stress the units, at least at the outset, is because it could be very easy to be like, oh, what's coming in is a constant 5 and just leave it at that. But that would be a mistake. So 5 picograms of dioxin per 1 gallon of water. But picograms per gallon is not what this rate needs to be expressed in. So I need to do something about this gallon, this volumetric rate. So how much, what's the flow rate of this water in the tank? This comes in at 4 gallons of water per 1 minute. So these gallons cancel. And what I get here is 20 picograms per minute. So that's what I wanted. And that's constant. I know what's coming into this tank is a constant 20 picograms per minute. All right. So what's leaving? So dd out over dt. So the water in the tank is well mixed. Okay, so I don't know how much dioxin is in the tank at any given time, but that's okay because I have a name for it. The amount of dioxin in the tank at any given time is D. And I know the water is well mixed, so the amount of dioxin that's going to leave the tank, it's going to leave like by ratio. So let's actually, I told you to keep the units in mind. So what's leaving is D picograms of dioxin. So how do I control for the concentration of that? So I know it's well mixed. So what's the ratio here? Um, so I'm losing 2 gallons of water. But as a proportion of what? How much water is in the tank at any given time? So this, I think we have to be a little more careful with. So we are told that the tank initially contains 200 gallons of water. But does it always contain 200 gallons of water? I don't think so. Um, so let's just think about how much water comes in and goes out of this tank every minute. So what comes into the tank is 4 gallons of water. What leaves the tank is 2 gallons of water, which means that every minute that goes by, um, the tank gains 2 gallons of water. So because of that, I think this denominator here is something that grows by 2 gallons every minute. So plus 2T gallons of H2O. Oh yeah, this will be per minute. Yeah, per 1 minute. Okay, so again, these units all wash out. So picograms per minute is what I'm trying to control for. Now it's a matter of kind of cleaning up um, my equation here. So ddT equals what? 20 minus 2D over 200 plus 2T. Every coefficient in this, second term here in my differential equation is even. So I'm going to rewrite this as dd dt equals 20 minus d over 100 plus t. Okay, so here's my equation, which I think we're done with number 1. Part 2, I want to solve this manually. So what kind of equation is this? So this is a first order linear, don't believe the variables are separable. So we have to rely on the new technique from this module. So that's going to come from integrating factors. So to facilitate that, I am going to move the d over 100 plus t term to the other side. So I get dd dt plus d over 100 plus t equals 20. So how do I find the integrating factor? So I want to basically think about this. I should have some function in t that's multiplied by d, which I do. My integrating factor, mu of t, is going to be equal to this, e to the integral of 1 over 100 plus t dt, which is equal to e to the natural log of 100 plus t. Typically, I'd have to do absolute values there, but I know that I'm not going to use values of t that are going to make this natural log negative, so I'm going to essentially ignore it. So e to the natural log of 100 plus t, or 100 plus t. So 100 plus t should be my integrating factor. So now what I'm going to do is multiply this entire equation, every term, by 100 plus t. So I get 100 plus t times d dt plus just d equals 20 times 100 plus t. Something I recommend once we've multiplied through by the integrating factor is, the whole reason we do that integrating factor is to make the left-hand side of this equation look like what comes out of doing the product rule of differentiation. So, and that product rule is always going to be the derivative of the product of what? The product of whatever your dependent variable is, in this case d, and whatever the integrating factor was, so 100 plus t. So let's make sure we think that happened. So how do you do the product rule of differentiation? Well, it's the derivative of d, so that's d dt times 100 plus t. So I have d dt times 100 plus t. That looks good. And then the other side should be basically the opposite. So plus d times the derivative of 100 plus t, which is 1. So I think the left-hand side looks exactly like I want it. So ddt of d times 100 plus t equals, and I'll go ahead and do this distribution, 2000 plus 20t. So now that we've done the integrating factor, it's called the integrating factor because it brings us to a place where the integral is possible. Integrate both sides, and I get d times 100 plus t equals 2000t plus 20t squared over 2, so 10t squared, plus a constant. Do I have the means to figure out what that constant is? Hopefully. All right, so do I have an initial value? A 400-gallon tank initially contains 200 gallons of water with a concentration of 2 picograms per gallon of dioxin. Okay, so I have the means to get it. So I know at time 0, then dioxin is equal to, it's not 2, it is 2 picograms per gallon times 200 gallons of water, so 400. So let's plug in those values. I have d times 100 equals 2000 times 0 plus 10 times 0. Oh, why did I not do that? D equals 400. 400 times 100 equals C. So C equals 40,000. All right, so did not budget my space enough here. Hopefully you'll agree that my bad drawing has served its purpose. And what's my equation here? D of T is equal to 2000T plus 10T squared plus 40,000 all over 100 plus T. So this is the analytic solution to my differential equation. Oh, so, but I was actually asked to evaluate that when this tank fills up. So when did this tank fill up? So it's initially half full, and I want it to get 200 more gallons of water in it. And I know that it fills up by 2 gallons per minute. So what value of T do I actually care about? So I think I care about T equals 100. So what is D of 100? D of 100 equals 2,000 times 100 plus 10 times 100 squared plus 40,000 all over 200, which gives me what? Let's find out. I get 1,700 picograms of dioxin. So that is my exact answer. So when I solve this analytically, I get 1,700 picograms of dioxin. So now let's do this. Let's figure out what happens when I set this up using Euler's method. So we're going to back out of this. I am not going to do a Euler's method with a step size of 1 by hand. So Euler's method calculator. Use Euler's method. Okay, so what is my equation? So I want to solve the differential equation. So y prime equals 20 minus, and I gotta translate this for my actual variables, y over 100 plus x. And I know that y of 0 equals, what did I say, 400? From 0 to 100 with h equals 1. So I believe this is all the parameters that I care about. Let's go ahead and hit enter. And hopefully we're close to something like 1,700. Okay, so when we use Euler's method under the conditions that I set forth, we get a value of 1701.51. So pretty close. So we have an error of 1.5, out of 1,700. So 1.51 divided by 1,700. That's, 0.08%. Very, very close. So that's Euler's method. The other approach that I asked you to approximate was Runge-Kutta 4. So Runge-Kutta fourth order method. So fourth order calculator. So Wolfram alpha again, good. So same equation, dy dx equals 20 minus y over 100 plus x from 0 to 100. H equals 1. All right, so let's see how this does. 1,500? That doesn't seem very close. Did I put this in the way I wanted? 20 minus y over 100 plus x with a step size of 1 from x equals 0 to 100. Oh, that's actually very surprising. Yeah, I got a value of y equals 1,500, but that is pretty far off. Let's try another one just to be be safe. Let's try Planet Calc. Y prime equals 20 minus, oh wait, I didn't give it an initial condition, did I? That's exactly what I messed up. So now that I realize my mistake, not the program's mistake, 20 minus y over 100 plus x. Y of 0 equals 400 from 0 to 100. H equals 1. This should be fine. It's exactly the same as Euler. Oh, wait, it says using Euler. That's why it's exactly the same. Okay. I'm going to make you deal with my problem one more time. Okay. Runge Kutta fourth order calculator. We're going to answer this hopefully only one more time. 20 minus y over 100 plus x. Y of 0 equals not 2, but 400 from 0 to 100. H equals 1. Show us what you got. 1700. So Runge Kutta did not even, I mean, as far as it rounded, didn't generate an error at all. So the error that it is reporting is this number right here, you know, times 10 to the negative 14. So very, very minuscule. I mean, the error we got from Euler's method was already very small. This one is, you know, almost inappreciable. All right, so that is all for discussion question 3.